I had it all in list 1 and list 2, and then I had 243, and we filled it with other stuff. You have the equation of the calculator, Michael? Oh! Well, that makes me very happy. Did you buy 2, Amber, as well?
Yeah.
Chances are you guys might, because your exam only had you use an Excel. Go ahead, Amber. What was it? Y equals?
Yeah. 20.78.
I'm going to call that 21 if it's okay. Go ahead.
Let me just give this to you.
Oh, you should know. Okay.
I don't know what I mean.
0.53 to the x. That's perfect. Here you go. That's all I need. I need a couple decimals. 21 times 0.53 to the x. Michael, yours too?
Pretty close, yeah.
Pretty close. Tom?
One's close, but I have like 19.4.
19.4. Mike, is that what you got as well? So either 21 or 19. Did you have 0.53 as well?
0.55.
Hey, you know what? Let's put them both down. It depends on which data points we left in and which we removed. There was an issue. We'll come back to that today. There's an issue with this kind of modeling where zeros cannot be in certain places. And depending on which data points you remove, I can see you getting either of these. They're very, very similar, are they not? They're very, very similar. Yes, extraordinarily similar. Do you guys remember how many students were in class the day we did the experiment?
22.
It was 22, wasn't it? Okay? So I'm going to put, these are our exponential models. That we got experimentally, which we're about to do with our decks of cards as well, which is extraordinarily nice. So it's okay that we got 2 different ones. They're pretty close to each other. Why are they called exponential models? What makes it exponential? What's the exponential part of it? Let's see this, okay? Good! Where is the, well, yes, very nice. We've got that asymptotic behavior. We actually ad nauseum got into that last time, which was awesome. Thank you for that, Aaron. Where is the variable? I'm so confused. Everything's over here. Yes, that's what makes it exponential. It's not a polynomial anymore like a quadratic or a linear was. Now your variable is an exponent. It's not a base like it was before, x squared, x cubed, x to the first. The x's before were bases that were raised to powers 1 or 2 or 3 or whatever. Now the exponent is the variable, or the variable is the exponent. So here's your variable now. And that's where it gets its name from. Now you might remember when we ran the regression in the machine, it spit back the general form y equals a parentheses b to the x power. And then it listed these numbers under. A was 21 or 19, depending on which one you got it. B was the 0.53 or the 0.55. So the idea is, what are these 2 pieces? I want to come back to that question, if it's okay. I'd like to get more data and run another model, or 2 even, if we have time. I think we have time to run 2. We'll see how time goes. So we'll use the deck of cards to generate some more data, and then run some models on the TI and see what we get. But I want to come back to this. And I want to make sure you guys are seeing what these numbers actually stand for, because they do stand for something very, very important. So let's create experiment number 2 while you guys are here. Experiment number 2. Now you're going to have to, this is only like 12 or 13 of us today. Yeah, 16 of us. There were 22 here. I'm going to put n equals 22 here. I'm going to put n equals 16 here. We're going to have to deal to ourselves, unfortunately. That's okay, though. So what you're going to do is, you're going to shuffle the cards up each time. And then just pull a card out of the deck somewhere. It can totally be the top of the deck if you want to. It doesn't matter if you're shuffling. So shuffle, take a look at the card. Okay? Somebody pick a suit.
Heart.
Hearts it is! I heard hearts first. If you get hearts, you stop. If you don't get hearts, shuffle up and do it again. Put the card back in. Shuffle up and do it again. Does that make sense? You guys see what I'm getting at here? So you're going to shuffle the deck, pull a card, look at it. If it's hearts, you stop. If it's not hearts, you keep going. Put the card back in, shuffle, do it again.
keep track of how many.
Please do, and just like the coin flips, keep track of how many times it takes you to get hearts. Fair? Everybody understand? Makes sense? So it's just like the coins, except now your coin has 4 sides. If that makes sense. Hopefully that makes sense. And if you think about it, a deck of cards really is a 4-sided coin. Yeah, for lack of a better image.
You mean because of all the suits?
Yes, and because there's the same number of each suit in the deck. So you're just as likely to get hearts as spades, as clubs, as diamonds.
I know.
I'm just saying, stop with hearts. Whoever voted for hearts, very, very nice. Okay? Hi. No. Very good question, Melissa asked. Don't worry about the suits that you are getting unless it's hearts. If it's hearts, stop.
Well, yeah.
Yeah, don't worry about the other ones. We'll come back to that. Yes, yes ma'am. Yes ma'am, yes ma'am.